In the last part of the series, we made good progress towards drawing our game objects with basic input controls, but we haven't done much on the core game logic. So let's think about what we need to do for the remainder of the game. We need to be able to move the tank, we want the enemies to be able to roam around on their own, we want to fire bullets to kill enemies, and we need game-ending conditions like when we kill all enemies or get destroyed by an enemy. Like I mentioned at the end of the last video, to implement those things, we need a strategy for collision detection, as it is super essential to all of these functionalities. So there are quite a few scenarios that we need to consider when we write our detection logic, but at a high level, we need to be able to detect when objects hit the screen boundaries and when they collide into each other and figure out the outcome. The bounce detection is relatively easy, so we're going to take a look at that first. Give me a few seconds to check in the code. And I'm going to include the movement code as well, just for a tank. The changes are fairly short, so let's dive right in. If you remember from last time, the tank struct has this move field that we are setting when processing directional keys. This is essentially a Boolean indicator on whether the tank should move towards its current direction. So for example, when you hit W while facing up, the tank will move up, right? So now we just need to take that information and compute the next location of the tank during our loop. And that's why you see I added a function call here to process the movement. And inside the tank move function, first of all, we want to make sure that the move field is set. And then after, we're resetting this field because we only want the tank to move once per key press. Then we're simply branching off into 4 directions with very similar code. As I said, we're adding bounce detections here. For example, in the move up case, if the top of the tank is at the screen's top, then we stop the tank by returning. Otherwise, we decrement the row field to move it up. Other branches are very similar, so I won't explain in detail, but do note that the row and column here is the top left of the tank. So when detecting in the down and the right case, we need to take the tank's own body size into consideration. So now when I run the game, I am able to move the tank, and I will be blocked when I hit the walls, which is expected. Now obviously, since there's no handling of object collision, so when I try to run into an enemy, I'm just going through them without any issue. And that's certainly not the right logic, so we're going to fix that next. Now, unlike bounce detection, detecting object collision is much more complex, as the location of the collision is dynamic and cannot be hard-coded into the program. When I was designing the program, there were basically 2 approaches that came to mind. One is kind of the obvious approach, where you would basically passing the pointers of other game objects while running the movement logic, and then just run a loop to check based on the location and object's hitbox to see if there's any potential overlap on every single pair. And this is a stateful approach, since every object now needs to be made aware of everything else in the game, which definitely works if you code correctly. And I might even say that this could be the more desirable approach if the game continues to grow in terms of complexity. But for this game, I ultimately decided to use an alternative approach that is simpler. And this is a technique that I would call it coloring. The way it works is that, well, let's take a look at the previous game screen. So let's think of this way. Inside the screen's border, we have either objects or empty spaces. And the spaces are just white space characters, right? Whereas objects consist of other characters. So in theory, wouldn't we be able to figure out whether they're objects by just looking at the characters around the current game object? And the answer is yes, but with some caveats. The first caveat is that sometimes white space characters exist inside the object's hitbox, right? For example, there's a white space character here inside the enemy, and even if we don't care about the inner part, here, this is also a white space on the edge. And if we take a look at the tank, well, 4 out of 5 characters on this row is blank. And that's the first issue. The second issue is that even if we may know that we're hitting something, it's hard to identify exactly what we're hitting, right? For example, all enemies look the same, and if we eventually have a bullet that hits an enemy, we can't just deduct the health on any object. We have to know exactly which one they were hitting, right? Which we can't do by just checking the rendered characters. So how do we solve these issues? Well, if you think about it, wouldn't it be great if we just draw every game object with a single unique character that fills its entire hitbox? Well, no, because then the game looks like garbage. But we can do a hybrid approach. We render the objects in the same way as before, but then in the backend, we fill the objects with unique characters for the purpose of running the game logic, and then redraw them before we render. Perhaps it is easier to explain with code, so I am going to check that in now. In this segment, we will start easy. We just want to be able to detect if we hit an enemy while moving our tank, and then also add the game over condition when that happens. So let's start here. In the tank move function, we're now going to use characters to detect objects, right? So now, for example, in the move up case, we're simply scanning the row above that tank, and if any character is not an empty space, we must have hit an enemy. So we're going to set the game state to lost, and that will end the game. And then similar things are happening in other branches with different directions. But to make that work correctly, as I mentioned before, we need to fill enemies' hitbox with concrete characters. And that is included in this fill enemy function. The logic is very straightforward. We just loop through an enemy's entire full body and then just fill it with character code equal to the ID of that enemy. And that is why I call this technique coloring, because when you visualize it, it is similar to essentially painting over an object with a certain color for identification. Now, I know the ID here doesn't matter for the tank itself, but remember what I said before. Eventually, we're going to need some method to detect which enemy we're destroying when bullets hit them. So now we just need to call this function during a game loop, so it is here. We got a simple loop to color all enemies. Now the important thing is that we're calling this after render, because this is meant for our backend only. We're not supposed to show it to users, right? We keep the colored objects around during the game logic, and then before we render again on the next frame, we need to redraw them so that the user sees no difference in their visuals. Then to properly end the game when someone has lost, we come down here to the main function to add a few more cases for different game states. My approach for the game ending is basically to rerun the title screen with a different banner text. So that's why you see this run title screen function being called in all branches with different banner text, which I also added here for either victory or defeat. So then a user is free to restart the game once they finish the round. To remind you where we jump out of the gameplay loop, here we are checking the game state and then returning from the run game function once the state is set to any other value, right? Similar to quitting. So then the main function can catch them and then change to a different screen. So just to quickly demo it. Now when I start the game, and then I will purposely try to run into an enemy, and you can see the game will be over. So I hope all that makes sense. Do take some time to digest it, as the coloring technique might seem a bit unusual. I chose this approach primarily for its simplicity, and it is also easier to debug because you can try to render the colored objects to see when things don't go the way you expected. It is also a stateless approach so that objects don't have to have knowledge on everything else in the game, so it is easier to compartmentalize and then decouple the code. The downside is that the logic becomes harder to control as you scale up your functionalities and add more objects, and you will start to run out of unique characters, which might require more layers of hack, and then eventually it will become very painful to maintain the code. So do consider the pros and cons when you are designing a game. Usually there's no perfect answer, just trade-offs. So now let's move on to the next thing. We already had the ability to lose the game, so to balance it out, we want the ability to win as well. And that requires us to give the tank the ability to shoot down enemies. So we'll introduce bullets and then the shooting functionality. The code isn't super hard, so let me just bring that in and then explain piece by piece. Okay, here we go. And on the top, we have definitions for the bullet object, and this is very similar to other objects. We come down here, and then the code for drawing the bullet. This is basically just a one-liner because the bullet is just a 1x1 hitbox represented with a start character. And then this active field here is meant to control the bullet's life cycle. So to explain this, well, the difference between the bullets and other objects is that bullets are created in response to player action and is dynamic, not simply spawned when we initialize the game. Basically, they come and go, so there's somewhat of a life cycle going on, unlike our tank or enemies, which will only be alive or dead. So the intuitive implementation is to have a dynamically sized list, right? And then you would add objects to that list when player fires a shot, and then take them out of the list once they hit something. Now, unfortunately, C is a very simple language, and it doesn't even come with an implementation of a dynamic list in the standard library. So, I mean, we can choose to write one ourselves, but for a game like this, I would just do a simple workaround. So we know there's a limit to how many bullets we can have in flight, which is pretty common in games like this, right? In a game loop, what we're going to do is that we're just going to initialize an array of bullets of that size, as we know there cannot be more than that amount that we need to control at any point. And then we use this active field to indicate if a bullet is currently in flight, which are all set to false at the beginning. And then once the player hits K, we are firing up this fire function, which then takes us here. And then you can see we're basically looping through the bullets cabinet and then looking for a bullet that's not active, making it active. And that's basically how we're going to enforce the bullet limit as well, because if all bullets are active, then this function does nothing, naturally. When we activate the bullet, we set its flying direction equal to the tank's current direction, and then the spawn point will also depend on the head of the tank, which again is calculated differently based on the tank's direction. And then this part is more optional. I wanted to add a cooldown to kind of limit the firing rate of the tank, so that a tank can only fire a shot, in this case every 3 frames. So until the CD field drops down to 0, the function also does nothing. And then the cooldown will be reset once we pass this, right? So going back down to the game loop, and you can see the cooldown is reduced by 1 every frame. And then we just draw all the active bullets in the loop, and that's about it. So now when I run the program, and then you can see I'm able to fire the shots, right? The bullets don't fly yet, and I am 100% aware of that. This is just a first step. And then they also don't destroy any enemies at this point, since we'll need the collision detection logic for that as well. But if I try to run into a bullet myself, I will actually die. Now remember when we move the tank, let me find here, right here. So if anything that we hit is not an empty space, we lose, right? I just think it's kind of funny that it happened to work out that way, even though this is not really strictly needed, as the tank in reality should never be able to catch up to its own bullet anyway. So it's kind of whatever. Now to make bullets actually work, we just need to add a few more things, and it's quite simple. So let me check that code in. And by the way, we're also going to implement the winning condition as well, because we will then be able to destroy enemies. All right. So the code is here, and mainly the thing to explain is just this bullet act function, which is similar to the function that moves the tank. But this is much easier as bullets only fly in one direction and has a very small hitbox. So this is the code to just kind of move the bullet in that specific direction. And then here we also do a round and bounce check to get rid of bullets that are hitting the wall. And then this is the collision detection. Remember, we have done coloring already for the enemies, right? So if a bullet's current position is not empty space, then we extract its code point and then use that to index into the enemy's array, right? Because this number essentially is the ID of the enemy, which is also its index into the array. And then after we found which enemy was hit, all we have to do is to deduct its hit points, right? In the game loop, we're just going to simply call this function on every bullet, and then things should just work. Because remember the draw function, let me find it. Yeah, so this is already checking the enemy's health before drawing, so enemies will be erased once their life goes down to 0. We then need to establish the winning condition, so here, we just run through the enemy's array and then setting the game state to 1 once we check that there's no enemy still alive. And then this will be propagated to the rest of the handlers. So to demonstrate this, I will make the enemy size 2 for now. And now when I start the game, and I will go all the way to the left, and I will try to put 2 bullets into this guy, for example, and then he will disappear, right? And then if I try to shoot this one down as well, and yeah, and I'll have a victory screen. And then I can restart the game if I so choose. So we're almost done. The last thing remaining is to implement enemy movement. Enemies move on their own, so we're going to handle them in a similar fashion as bullets, but there are some additional complexities. Let me just bring in the last segment of our code and kind of just explain as I go. And this is actually harder than most of the logic we talked about before, so please do bear with me here. And I'll try to slow it down as we walk through. So the additional code structurally is not bad at all. We just introduced this enemy act function that's also invoked on every enemy during each frame. It's similar to the bullets. The life check here is pretty obvious, and then I also put a cooldown on the enemies to have a way to slow them down, and it's something that we can tweak when we're tuning the game speed. The way it works is very similar to how we throttle the firing rate of the tank, so I'm not going to over-explain here. And then here is where we kind of introduce the AI for them. And then it's basically all controlled by RNG. And they have 5 directions, including a stationary value, which means that we just pause on this frame. And then when they're stationary, we use this function to kind of assign a random direction on the next frame, which can still be stationary. Okay, so after that, if we are seeing that they're moving, then we again branch off to different code based on their direction, right? So let me just collapse all these sections, and let's just first concentrate on a single case because they're not that different. Now before I dive in, let's first think about what do we need the enemies to detect. Well, they need to detect if they hit the tank while moving. They need to be able to detect borders and then turn around if they hit them. They need to detect their comrades and then not to collide into them. And then they can also try to detect bullets as well, but since bullet has a very small and size 1 hitbox, the detection logic on the bullet itself should be sufficient, so we don't need to do extra code for that. Now the complexity here is that the outcome of the collision is different on the tank versus other things, right? Because when enemies hit the tank, we lose the game, but if they hit other things, then they should stop and then try to pivot to a different path. And that's why essentially there are 2 separate cases here. Remember the coloring technique that we have introduced for detecting enemies. We will now add the fill tank function that also colors the tank with a special code, and then it will also be called in the same place before we run the game logic, right? So now the enemies just need to look ahead in their current position, and if they see a tank char, then they may destroy us. Otherwise, if they see other non-space characters, then they know they're about to hit something. So we set the collision flag to true. Now after this detection loop, if there's no collision, then the enemy will proceed to move in that direction, similar to other object. Now this is where it gets a bit more complex. Before I move the enemy, I'm also filling out the row or the column in front of that with a dummy character E. And you probably wonder why. And this is an edge case which I also didn't realize when I first coded this, because the thing is, we're processing the enemies sequentially, right? One at a time. So imagine what happens if you have 2 enemies, they're right next to each other, let's say from left to right, but there's one empty space, one empty column in between. right? And then the left one tries to move right, and then you have the right one tries to move left. Well, if we don't do this, then the logic will technically allow that to happen because there's an empty seat for both of them. But once they actually move, they will collide into each other, and then the player will see that they overlap temporarily for a moment. And this is a scenario that we want to avoid, kind of like a race condition where you have two things that both trying to occupy a single space at the same time, and then we must decide a winner for them. So that's why I added this, so that if some other enemy later wants to take the same spot, then he will know that this is already occupied and then back off. And then we also want to do the collision check before we destroy the tank because, well, there's another edge case that we have to consider. Imagine if we have a tank and an enemy side by side. They're not touching, just side by side from left to right. And another enemy is coming from the bottom, let's say right in the middle of the two, and trying to destroy the tank by going up. So when it goes up, it touches both the tank and the other enemy as well. In that case, I want to prevent the tank from being destroyed as well because technically the enemy on the bottom is blocked by the other enemy on its path. So that's why when there's collision, we don't initiate any other logic other than just telling that enemy to back away. And then you can see when there is a collision, we are again going to select a random direction for that enemy so that it will walk away from the site. Now this alone works just fine, but it does make enemies a bit too predictable as you know that it will just head down a single direction unless there's collision. So I also introduced a bit more randomness here to basically have a % chance that an enemy can just randomly decide to switch direction on its own. The chance is controlled by this stability value. The larger the value, essentially the more stable it becomes and then less likely to change direction on every frame. And then these other branches are essentially the same logic, so I won't explain here, I'll just leave that for you to read on your own. And then when we scroll down, there are only two extra lines here. This one is to call the function on the enemy, and then we also call the color function on the tank, and then we're done. Now when I run the code, you will see that we have the complete game, exactly the same as shown in the ending of that first video. So those of you still watching, I really appreciate you sticking around. Definitely let me know if you have any comments or questions, or if you think my C code sucks. C is not my best language. I probably rank it maybe the 4th place of the languages I know, but I hope you find this interesting and maybe this gives you some inspirations to go build something on your own. The point of this is not to have you replicate the same game. This is obviously just a stupid game that nobody will ever play, but it does show some interesting concepts and possibilities. And anyone who is an experienced software engineer should know that in this field, knowing something is possible is way more important than knowing exactly how to do it. Because if you don't know it is possible, then you never get started. But once you know that it is possible, it is just a matter of time and commitment to figure out the details on implementation. So it is up to you on what you want to do on the next step. If you want a similar practice, maybe try to build something like a Tetris clone on the same platform, or if you just want to scale up your own project, either at school or on your own job. For example, you can think about the design choice that we made on the collision detection mechanism. Is that still the best choice as you build more and more functionalities on the real game? How many edge cases would you encounter and how would you solve them while keeping your code clean? Do you want to abandon coloring at some point and then pivot to object-on-object detection? And how would that scale up if you have to check every single object pair? Maybe that works with 10-20 objects, but if you have a complex game with thousands of things that can collide, and you have an algorithm that scales quadratically, it doesn't matter how fast your programming language is. Once you reach a certain scale, right, your game will grind to a halt, your CPU is going to start to scream, and you are going to have very, very unhappy customers. So at that point, you might want to build an entirely separate module to just handle collisions on the map, rather than having objects do this on their own. So those are the ideas and the trade-offs that you want to be thinking about on a real project. So I hope that no matter what stage of career you're currently on, you are able to take away something that will help you become more thorough and then improve not just your skills, but the mindset that you need when you grow as a programmer. And that's all I have for now. Thanks for watching.